Okay, welcome back. We're talking about comparing sort algorithms, and so the classification could be like stable and unstable, and whether or not it does a divide and conquer slash, recursive kind of a routine. I mentioned that the insertion sort is actually pretty decent, but only for smaller sizes. Nobody uses the bubble sort. Shell sort is actually pretty good if memory is kind of short at a premium. Radix has good implementation, but if it's skinny and tall, it's okay. But if it's wide and squatty, it's not. Heap sort has very predictable runtime, which is good. And you would use the heap sort when the worst case is more likely than average. That's a good way of describing it. In other words, when things are completely random, the worst case scenario might be better, than the average case. So that's a good definitor. The merge sort is a stable one, and it has a way, because it's broken up into chunks. You could do some parallel programming. In other words, when you broke the thing up into a piece and you sorted this piece, you could pass that off to another machine. Now, we're not doing that, but it definitely lends itself to having some parallel operations going on. So if you had lots of CPU cores and speed was important, man, you'd pick this guy. Okay, he's pretty cool. However, the in-place versions there's lots of variants on these guys. The in-place versions are not stable. If you're doing it to another array, then it could be stable. The quick sort. This one works really well when things are like partially sorted, or another way to look at it, when average is more likely than worst. Okay, then that makes for a good one. It's not necessarily stable. So let's talk about this for a minute. The C language has a built-in sort routine. So are you a little bit curious which sort algorithm does it use? Well, it follows the rules that I just talked about. It uses a thing called an introspective sort, which is kind of a fancy term for, I don't know yet, I'll get back to you. What it does is it looks at the list and then picks the sort technique based upon how big the thing is. And so, it breaks things up into partitions. Okay, I'm not going to get into what a partition is. Okay, so just bear with me. If the partition is less than 16, it's going to use the insertion sort, because the insertion sort is pretty doggone efficient as long as the numbers aren't very huge. Well, 16 is clearly a small number. And then at the other end, if the number of partitions exceeds 2 times log n, okay, then we're going to use a heap sort, because the heap sort is one of those has, fairly predictable runtime. And then, so at this end, we're going to use insertion. At that end, we're going to use heap, and everything else in the middle is going to use quick sort. So it uses internally 3 different sorts depending on which, depending on the size of the array being handed to it. Isn't that pretty doggone cool? Okay, so one more time. Which of the big O's should I actually be shooting for? Okay, I know this sounds kind of dumb, but yeah, you guys need to figure this out about which one hugs the x-axis the most. Yeah, I kind of sort of need to know that. Okay, so we have reached the end of this, and I hope you guys have learned an awful lot about sorting, and particularly the thinking behind it. Yes, you're going to have to mechanically do these sort routines in a term project that's coming up, but more than that, you're going to need to noodle it out. You need to be able to tell me why, when I have backwards a reverse sort in each one of these algorithms, how are they going to behave and why? Yeah, there's an awful lot of thinking along with this. Okay, we've reached the end of this chapter, and I'll see you guys again in the next chapter.